Hi all. In this video we will study set identities. These are basic set theory rules that we will use again and again. So it is good that we study them and we also see their proof. Okay. So first of all, let me tell you that we will denote this universal set. Okay. So let's denote the universal set by the symbol M. So this symbol we will use for universal set. Okay. So actually we are using this symbol for universal set so that you do not confuse because of union and universal set. Okay, so for example, if I write like this, a union M, what it means? It means that set A union, this is the symbol for union and this is the universal set. So what will be A union M? That will be M, because if you have any set A, let's assume this is your set A and this is the universal set, this is the set A, then what is A union M? A union M means all the elements of A comma M. So this is the A union M. So that is equal to M. So this is the idea. Now let's see this set identities. The first is identity law. What is the identity law? So this is basically what this identity law says is that, okay, like if you have, for example, in number theory, what we have in a number theory, when you study the numbers, okay, when you study the numbers, then in number theory we have this. In number theory we have, for example, if you have any number n, okay, then plus what should I do such that I get n? Similarly, if I have any number, what should I multiply such that I get n? So you can notice, with any number if I add 0, similarly with any number if I multiply 1, then you can notice these things I will get. N plus 0 is n into 1 is n. So these are called identity elements. So basically this is called identity element of addition. This is known as identity element of addition, for addition or addition. Okay, and this is the identity element of multiplication. So basically this is the identity element for multiplication. Okay, for multiplication. So this is the idea. So basically this identity law, what it says that if you have a set, so let's assume you have a set A, then what should I union? Okay, what should I put here? What should I put here such that I get A? So what should I do? A union something, A union something, so that I will definitely get A. Yes, that is basically phi. A union phi is A. Similarly, A intersection, what should I write here so that I get A? Okay, what should I put here? I should put universal set. So this is the idea. This is the identity law. Identity law means A union phi is A intersection universal set is A. And the proof is very simple. You can prove by Venn diagram. So if you have this Venn diagram, this is the universal set and this is the set A, then you can clearly see what is A union phi. What is A union phi? A union phi is A, because in phi we don't have any element. A union phi means all the elements of A, all the elements of phi. There is no element in phi, so all the elements of A you will get. Okay, what is A intersection M? A intersection M is basically A. Only this is the A intersection M, because this is the common area. This is the common area of A comma M. M is the universal set. So this is the identity law. Now remember, what is the definition of identity element? This you will study in the group theory, but let me tell you that identity element is like this. Identity element. Okay, so identity element E for operation. So if you have some operation, okay, then what is the identity element for that operation? Identity element E for operation hash. What this means? This means like this. Okay, that you have some X hash, okay, this E. If I do this X hash E, then I will get X. Similarly, if I do E hash X, then I will get X. This is the definition of identity element E for operation X. For example, as you know, okay, like this, okay, for multiplication, the identity element is 1. For addition, the identity element is 0. For union, the identity element is 5. For intersection identity element is universal set. Okay, so this is the idea. So from this idea you can notice that if E is the identity element, then you can notice this identity element will not change, will not affect the operation. This one does not affect multiplication. N multiplied by 1 is n. So this 1 does not affect multiplication, 0 does not affect addition, phi does not affect union, and universal set does not affect intersection. So basically identity element does not affect this operation. So if E is the identity element, then X hash E is X and also E hash X is X. So this E does not affect the operation. This will does not affect the operation. Like 1 does not affect multiplication, 0 does not affect addition. So this is the idea. So let me ask you this question. Is there any identity element for symmetric difference? What is the identity element for symmetric difference? So what is the identity element for symmetric difference? Okay, basically the question is, if you have a set A, then set A, what should I write here? Okay, set A, what should I write here such that I get A? Okay, remember, what should I write here such that I get A? This is the idea. So what should be this? Let's assume, okay, set, okay, what is this X? Basically the find X. Similarly, remember, this also should happen. Okay, so now finally, what is X? So this is the question, what is X? Do we have any such X? So that asymmetric difference X is A. So what is that? So here the X is basically empty set. You can check it out, because if you have any set, okay, if you have any set, then symmetric difference, okay, then what that is basically, that is basically A minus phi union phi minus A. This is the definition of symmetric difference. We know that A symmetric difference B. Symmetric difference means exclusive OR. Okay, so you can also say that this is exclusive OR. What this means? This means that A minus B union B minus A. So what is A minus phi? A from, okay, from A, if you remove phi, then you will get A union phi minus A is A. Phi minus A is phi, so A union phi, that is A. So you can clearly see that, okay, A symmetric difference phi is basically A. So this phi does not affect the symmetric difference. Similarly, you can notice that phi symmetric difference A is also A. So I can say that identity element for symmetric difference, that is basically phi. This empty set is the identity element for symmetric difference. Okay, so this is the rule. A symmetric difference phi, that is A. Phi symmetric difference A, that is A. This is the definition of symmetric difference that we have already seen. Okay, now what is the symmetric difference for, what is the identity element for set difference? Okay, basically the question is this: do we have some element, do we have some elements such that we get A? Yes, the element is phi. Okay, so that element is phi, but there is a problem here. What is the problem? A minus phi is A, but you can notice phi minus A is phi. Okay, so you can notice that is not A. So this is the idea. So from here I can say there is no identity element for set difference. Remember, identity element definition is this. Okay, you can notice the identity element should have these two properties. This should also happen, this should also happen. Both these things should happen. Okay, this and this means X hash E should be X, E has X should be X. So these two things must happen. But you can notice in the set difference, in this set difference, I can say that A minus phi is A, but phi minus A is not A. Phi minus A is phi. So I can say identity element for symmetric difference, okay, there is no such identity element. Okay, no identity element exists. So I can say no identity element exists for set difference. So this is the concept, but this is important that A minus phi is basically A. So if you want to remember, you can remember this, that any set A minus phi, that is basically A, and phi minus any set, that is basically phi. And also A symmetric difference phi is basically A, phi symmetric difference A is basically A. And okay, so this, okay, anyway, this is the concept. Let's see what is the identity element for cross product. Basically the question is A cross, what should I write here such that I get A, such that I get A? What should I write here? A cross, what should I write here such that I get A? There is no such element, there is no such element, because what will happen, see, if A is like this, A comma B, then you can notice if you do the cross product with anything, okay, whatever you have here, if you do the cross product with anything, you have set A is A comma B. In this set A you have two elements. Now whatever I write here, whatever I write here, like if I write for example set B, then what you will get in the cross product, you will get ordered pairs. Every element of this cross product, that will be ordered pair x comma y, where x is coming from A and y is coming from B. So you can see that, okay, there is no identity element for cross product, because if you have a set A, then this is your set A, but in the cross product you will have ordered pairs. In the cross product, every element will be ordered pair x comma y, where x is coming from A and y is coming from B. So that's the point. So I can say this A, this can never be equal to A cross B. Okay, so this is the idea. A is never equal to A cross B. So that's the reason I can say that there is no such identity element. So what is the identity element of cross product? And the answer is no identity element exists. So what is the answer? Okay, no identity element. There is no identity element because this is the fact that A can never be same as A cross B. Because if you think, for example, 5, A cross 5, A cross 5 is 5. Because what is the definition of A cross B? A cross B is basically set of ordered pairs. You have elements in A, elements in B. So what is cross product? Cross product is basically set of ordered pairs, okay, where the first element coming from A, the first element comes from A, and the second element comes from B. So in the cross product, you will always get ordered pairs. Every element will be ordered pair. Okay, every element is an ordered pair. So you can clearly see A cross 5. In 5, you don't have any element. So there is no element here. Okay, in A cross B, we have pairs. We have pairs of elements where first element is from A, second element from B. But in this 5, in this empty set, there is no element. So I can say A cross 5, that is basically 5. Okay, A cross B, if you do A cross B, then that will definitely contain set of ordered pairs. So that can never be same as A. That is never same as A. So I can say A cross B can never be same as A. A cross B, okay. Actually, when A is 5, then A cross B can be. So I can say, okay, this is the point. So I can say A cross B is equal to A if and only if A is equal to 5. Okay. So if and only if A is 5. A cross B is equal to A if and only if A is 5. If A is 5, then this will happen. And if this is happening, then it means A is 5. So this was the identity property, and this is important. So identity property means A union phi is A intersection universal set, that is basically A. Now the next is domination law. The domination law says that A union, okay, so this is the domination law, that if you have this set A, this is your set A, this is the universal set, then what will be A union M? A union M will be basically M, because A union M means all the elements of A comma M. So A union universal set will be universal set. And what is A intersection phi? The common elements. There is no common element because phi does not have any element. So these two rules we have. A union phi, A union universal set is universal set. A intersection phi is phi. We have already seen that A minus phi is A. We have already seen all these things. So all the related concepts, all the related rules I am writing here. A minus phi is A. Asymmetric difference phi is A. Phi minus A is phi. Okay, so similarly A cross phi is phi. So all these concepts are related, but anyway, these two rules are called domination law. This is the name for these two rules. A union universal set is universal set. A intersection phi is phi. What is the idempotent law? Idempotent law means basically A union A, that is A. Okay, so let's see the idempotent law. Okay, let's see idempotent law. So this word is very important in other subject, like when we studied dbms, at that time this word is going to be important. Idempotent. Okay, what is this word? This word basically means repetition does not matter. Okay, so basically if you have some operation hash, this operation hash is idempotent if and only if x hash x is x. So basically the idea is this. The idea is that you can repeat this x hash x, so that should be x. So this is the definition of idempotent law. For example, tell me addition is the, can I say addition is idempotent? Can I say addition is idempotent? Idempotent. Can I say addition is idempotent? The answer is no. Addition is idempotent? No. Because what is x plus x? X plus x is not equal to x. X plus x is equal to 2x. For example, you can notice, okay, 3 plus 3, that is not equal to 3. So I can say addition is not idempotent. What about multiplication? Multiplication is also not idempotent. Similarly, you can notice, okay, multiplication is also not idempotent. Not idempotent. So multiplication, addition, all these operations, like for example 3 multiplied by 3, this is not equal to 3. The definition of idempotent law is basically the operation hash is idempotent if and only if, okay, x hash x is equal to x. So in the linear algebra, in dbms, in other subject, you will use this word idempotent. Okay, now let's come back to our set. So let's assume you have a set A comma B. These are your set. Then can I say union is idempotent? Okay, let's see. Can I say union is idempotent? Can I say this? Union is idempotent? The answer is yes, because A union A, that will be basically A. Remember, A union A, that will be basically A. So union is idempotent. Similarly, intersection is idempotent because A intersection A is also A. A union A is A. A intersection A is A. So I can say union is also idempotent. Intersection is also idempotent. Okay. So this is the idea. Intersection is also idempotent. Now, what about set difference? Can I say set difference is idempotent? So this is the question. So tell me, can I say set difference is idempotent? The answer is no, because you can see that this is set difference. What is A minus A? A minus A is not equal to A. So basically A minus A is 5. So I can say A minus A is not equal to A. So that's the reason I can say that set difference is not idempotent. Symmetric difference, can I say that is idempotent? What is A symmetric difference A? That is also 5. So that is also not equal to A. Asymmetric difference A, that is also not equal to A. So this symmetric difference is also not idempotent. So this is also no. What about cross product? The cross product is also not idempotent because you can notice A cross A is not same as A. In A cross A we have ordered pairs. In A we have, okay, we don't have ordered pairs. So for example, if A is this, okay, then what is A cross A? A cross A will be A comma A. So you can notice A is not same as A cross A. So I can say these operations are not idempotent. So this was the idempotent property. A union A is A. A intersection A is A. This is the idempotent law. What is the complementation law? That is very simple. A complement whole complement is A. Okay, so if you do A complement and then again you do complement, then that will be same as A. This is the complementation law. Next, similarly, A intersection A complement. What is that? That is phi, because there is nothing common between A comma A complement. So this A intersection A complement. What is common? What is common in A comma A complement? That is phi. Nothing is common. And what is A union A complement? That is your universal set. That will be universal set, because A, you can notice that if this is A, if this is set A, so you can notice this red area is the set A, and this area, this yellow area is a set A complement. So you can notice A union A complement, that is universal set, and A intersection A complement, that is phi. Okay. The next rule is commutative law. What is this commutative law? So if you have some operation, this operation can be anything. If you have some operation has, this is called commutative if and only if x has y, that is equal to y has x. Okay, so if this happens, means the order does not matter. Like x has y is equal to y has x, then we will say that this operation has is commutative. For example, addition is commutative. You can notice 2 plus 3 is equal to 3 plus 2. So I can say A plus B, that is same as B plus A. So addition is commutative. Multiplication is commutative. So this multiplication is also commutative. Now in set theory, what you can say? Okay, so let's assume in set theory, if you have in set theory, can I say, for example, let's assume you have a set A comma B. Then can I say union is a commutative? What can you say? Like A union B. Can I say this is same as B union A? Yes, this is correct, because what is A union B? That is set of all elements of A comma B. B union A means set of all elements of B comma A. So basically merge all the elements of A comma B, merge all the elements of A comma B. So both are same. A union B is same as B union A. Similarly, A intersection B is same as B intersection A, because both will give you the common elements. Okay, so this is the idea. So I can say union is commutative, intersection is commutative. Okay, what about symmetric difference? Can I say A minus B is the same as B minus A? This is not correct. So symmetric okay, this set difference is not commutative. And what about symmetric difference? Yes, symmetric difference is commutative, because a symmetric difference B, that is same as B symmetric difference A. Yes, that is commutative. Okay, so you can clearly see, if I have, let's assume you have set A, this is set A, and let's assume this is set B, then what is this area? This area is A minus B, and what is this area? This area is B minus A. So you can clearly see A minus B is not same as B minus A. So that's the reason I can say this set difference is not commutative, but symmetric difference is commutative. Because what is symmetric difference? This is the symmetric difference. A symmetric difference B, that is basically this A minus B area union B minus A area. Okay, so basically this area union this area, this is your symmetric difference. And symmetric difference is a commutative, because if you do B symmetric difference A, then also you will get this same area, this area union this area. So that's the point. So B symmetric difference A, that is same as A symmetric difference B. Okay, this is the concept, this is the rule of commutative. So union is commutative, intersection is commutative, symmetric difference is commutative, and you can notice cross product is not commutative. You can clearly see A cross B, that is not same as B cross A. For example, if you have a set A, let's assume your set A is A, and let's assume your set B. Okay, so what is set B? So let's assume set B is B. Then what is A cross B? In A cross B, we will have ordered pairs, okay, where first element coming from A, second element coming from B. And what is B cross A? B cross A, we will have first element will come from B, second element will come from A. So you can notice these are basically not equal. These are not equal. So I can say this cross product is also not commutative. Okay, next is associative law. What is this associative property? So this is the definition of associative law. Associative law means you have some operation has, that has is associative if and only if that this operation has is associative if and only if A has B has C. If you have this type of situation, basically this type of situation has, okay. Okay, so if you have conjugative has, so this operation is associative if and only if in this type of situation, okay, whether you do this first has first or you do this second has first, these two must always be same for all A comma B comma C. Okay, so I can say for all A comma B comma C, this should happen. This should happen that whether you do this first has first or whether you do this second has first. Okay, these two things must always be same for all A comma B comma C. Then we will say that this has is associative. Okay, for example, addition is associative. For example, if you have, let's assume you have n plus m plus, okay, t, then you can notice that, okay, whether you do this first addition first or whether you do this second addition first, they are same. So addition is associative. Similarly, multiplication is also associative, because you can notice that whether you do this first multiplication first or you do this second multiplication first, the answer is same. So addition is associative, multiplication is associative. But in set theory, okay, let's come back to set theory. In set theory, if you have, let's assume you have set A comma B comma C, then can I say union is associative? For example, can I say that A union B union C, okay, can I say this is the same as this? Like, okay, A union B union C means whether you do this first union first or you do this second union first, yes, that is correct. Because what is A union B union C? That is basically merge all the elements of A comma B comma C. So this will merge all the elements of A comma B comma C. This will merge all the elements of ABC. So of course they are same. Similarly, intersection is also associative. If you have intersection like this, okay, then whether you do this first intersection first, okay, or you do this second intersection first, both are correct. So this and this, so I can say intersection is also associative, because what this means, A intersection B intersection C, this is the common elements of ABC, common elements in all of them, common elements in A B C. Similarly, this is also common elements in ABC. So yes, they are same. So I can say associative, I can say that union comma intersection, these are associative. But what about symmetric difference? Okay, so you can I say that A minus B minus C, okay, can I say this is symmetric difference? Can I say this is symmetric difference is associative? Symmetric difference is not associative. This is clearly not associative, because for example, if you take, let's assume you have A, let me give you example. So let's assume A is 1, okay, and let's assume B is also 1 and C is also 1. Now in this situation, what will happen? In this situation, this A minus B minus C, what this will become? A minus B will be 5. Okay, so this A minus B, that will be 5. This A minus B will be 5. So this will be basically 5 minus C. Okay, because from A, if you remove B, then that will be 5. 5 minus C, that is basically 5. So this this LHS is basically 5. And what is RHS? A minus B minus C. Remember, this is A minus, what is B minus C? B minus C is 5. So what is A minus 5? That is A. And what is A? This is A. So you can clearly see these are not same. Okay, these are not the same. So what I can say? I can say symmetric difference is not associative. Okay. sorry, set difference is not associative. What about symmetric difference? Can I say that a symmetric difference b, symmetric difference c, can I say this and this they are same? This is my question. Can I say a symmetric difference b, symmetric difference c, or this and this, can I say they are same? Yes, they are same. You can very easily prove it. Basically, what is the idea? Okay, so you can just, the proof you can very easily see. So by Venn diagram you can prove it. You have set A, B, C. Now in this Venn diagram, if you have three set A, B, C, then how many area are there? Total 8 area we have. Area 1, area 2, area 3, area 4, area 5, area 6, area 7, area 8. So total 8 area we have. Now let's see what is the area of A symmetric difference B. Okay, so this, let me call this LHS. Let me call this complete thing LHS. And let me call this complete thing as RHS. Okay, so this complete expression let me call RHS. Now what is the area of asymmetric difference B? Asymmetric difference B, that means exclusive elements of A comma B. That means A minus B union B minus A. Means those elements which are in exactly one of these set. Okay, A symmetric difference B means those elements which are in A but not in B, or which are in B but not in A. So basically those elements which are in exactly one of them. So what is this area? That area will be 2 comma 5. Asymmetric difference B I am finding, so that will be 2 comma 5 comma 3 comma 6. So this is the asymmetric difference B. Okay, what is, now you have asymmetric difference B. Now what is asymmetric difference B symmetric difference C? What that will be? Basically this symmetric difference C. So what is the area? Means, okay, means either exactly here or exactly in C. So that is the idea. Asymmetric difference B is this. So what is this? Basically 2, 5, 3, 6. This symmetric difference C. What is the area of C? Area of C is 4, 5, 6, 7. This is the area of C. So what is the symmetric difference of these two? 2, 5, 6. Okay, 2, 3, 5, 6, 4, 5, 6, 7. What is the symmetric difference? Symmetric difference means that area which is exactly in one of them. That area which is exactly in here, or that should be here but not here, or that should be here but not here. So basically this symmetric difference, this, that means that area which is in exactly one of them. So what is that area? That is area is basically 2, okay, comma 3, comma 4, okay, so comma 7. You can notice this 2 is here, 2 is not here, and this 3 is here but 3 is not here. So from similarly 4 comma 7. So this is your LHS. Actually I can say this is the LHS. LHS is 2, 3, 4, 7. Okay, now you find what is the RHS. So we have found LHS. Now let's find RHS. In RHS, what is B intersection B symmetric difference C? So let's find it out. So what is B symmetric difference C? Means this B symmetric difference C. So that will be the area which is in exactly one of them. Okay, so that will be 3 comma 7 comma 4 comma 5. Okay, so this area is B symmetric difference C. Now what is A symmetric difference B symmetric difference C? What is that? So you know the area of A. Area of A is 2578. This is the area of A, 2578. Symmetric difference B symmetric, okay, B symmetric difference C, that is basically 2457. Now what is the symmetric difference of these two? So again that will be those area which is in exactly one of them. So that will be 2, okay, that no, will not be 5, that, okay, so that will be 8, that will be 4, and that will be, so okay, that will be 3. So this is the idea. So 2, 3, 4, 8, 2, 3, 4, 8, and here we have, so actually we made a mistake here. The area of C, that is basically 4, 4, 5, 6, 8. So what we will get here, we will get, this will be 8. So you can notice the LHS area is 2, 3, 4, 8, and the RHS area is also 2, 3, 4, 8. So this RHS area is also 2, 3, 4, 8. So I can say yes, symmetric difference is associative. So this is the point, symmetric difference is associative. Using Venn diagram you can very easily prove. So I can say that A symmetric difference B symmetric difference C, that is same as, okay, whether you do this first symmetric difference first or you do this second symmetric difference first, okay, that is both are same. Okay, so the proof is very simple. See, this is LHS, this is RHS. You can make the proof. You can make the Venn diagram. In the Venn diagram total 8 area we have 1, 2, 3, 4, 5, 6, 7, 8. Now what you can do, you can find the area of A symmetric difference B, that will be 2536. Now you can find the symmetry difference of this and this, so that will be 2348. Similarly you can do for the RHS. So the RHS area is 2348 and the LHS area is 2348. So I can say LHS and RHS are equal, so I can say symmetric difference is associative. Okay, so this is the point. The next is distributive property. What this distributive property says, that basically A union B intersection C. If you have this type of situation, A union B intersection C, then you can distribute this union over this intersection. So what you can do, you can do this, that A union B intersection A union C. This is called distributing this union over this intersection. So this union you can put inside basically A union B. You can do this A union B intersection A union C. So this is correct. You can prove by using Venn diagram. You can create the Venn diagram and you can prove it. Similarly, this is also correct. A intersection B union C. So here what you can do, you can distribute this intersection over union. So what you will get, you will get A intersection B union A intersection C. So this is called distributive property. And the proof is very simple. You can prove by Venn diagram. Okay, so you can do it yourself. Okay, this is not very hard. So this is very simple. Distributive property means A union B intersection C. So this union you can distribute over intersection. Similarly, this intersection you can distribute over union. So A intersection B union C means A intersection B union A intersection C. Okay, so this is the distributive property. The next property is absorption law. Okay, the next is absorption law. What is this absorption law? Basically this is saying that A union A intersection B, that is A. Okay, so A union A intersection B, that is simply A. Similarly A intersection A union B, that is also simply A. So these are also very useful. Many times these will be very useful, and the proof is very simple. See, if you have this, let's assume this is your universal set, this is set A, this is a set B, then you can clearly see what is A union A intersection B. Remember, this is A intersection B. Okay, so what is A union A intersection B? This area is A intersection B. So finally I can say A union A intersection B is simply A. Okay, this is A and this is intersection, so I can say A union A intersection B is simply A. Similarly, A intersection A union B. Okay, so this is A union B. This is the A union B intersection A. Intersection A. So the common area between A and A union B, that is basically A. So this is the idea, and this is very useful many times. This I can also, for example, if you have B union A intersection B, what that will be? That also that will be B. Okay. Similarly, if you have B intersection A union B, then that will be B. So this is the idea of absorption law. Okay. The last is De Morgan law. What is this De Morgan law? This is also very important. This is extremely important. So what this De Morgan law says? This says that if you have A union B complement, okay, so that will be basically A complement intersection B complement. Also, if you have A intersection B complement, then that will be A complement union B complement. Okay, so this is the law of De Morgan. This is the De Morgan law. And the proof is very simple. See, okay, let's understand the proof, the analytical proof. Let's understand the analytical proof. See, A union B complement. Okay, what this means? What this means? So, for example, if X belongs to A union B complement, then what this means? If X belongs to this, then I can say that X does not belong to A union B, because we already know this, that if some element X belongs to A complement, then I can say that X does not belong to A. Similarly, if X does not belong to A, then I can say that X belongs to A complement. So this is the idea. So I can say if X belongs to A union B complement, it means X does not belong to A union B. X does not belong to this A union B. Okay, X does not belong to A union B. That simply means that X does not belong to A and X does not belong to B. Now, X does not belong to A, it means X belongs to A bar, and X does not belong to B, it means X belongs to B bar. X belongs to A bar, and x belongs to B bar, so I can say x is common in A bar and B bar, so I can say x belongs to A intersection B bar. So what we have done here, we have proven that, okay, so we have proven that if any element is here, then that element is here. If any element x is in A union B complement, then that element will also be in A complement intersection B complement. So from this, actually what we have proven, from this we have proven that this is a subset of this. But remember, we also have to prove the other direction. The other direction we also have to prove. So from here we have proven that A union B complement is a subset of, okay, A intersection A complement intersection B complement. The other direction also you can prove. So if x belongs to A complement intersection B complement, then what can I say? Then I can say x definitely below, x is common in A complement, x is okay, x is also in B complement. X is in A complement, it means x does not belong to A. X is in B complement, it means x does not belong to B. Okay, x does not belong to A and x does not belong to B, so I can say x does not belong to A union B. X does not belong to A union B, it means x belongs to A union B complement. Okay, so this is the idea. So from here what we have done, we have proven that A complement intersection B complement is subset of A union B complement. So from these two, okay, so from these two I can say, so we can say that A union B complement is basically A complement intersection B complement. Similarly, you can prove the same method you can apply, and you can prove that A intersection B complement is equal to A complement union B complement. Okay, and this De Morgan law is actually very important. Okay, so because in the De Morgan law, if you notice what is happening in the De Morgan law, if you notice what is happening, first of all, basically the De Morgan law is applied for complement. Basically, in the De Morgan law, you are finding the complement, and this expression only has union comma intersection. So this is the idea. So I can say that if you have some expression, so let's assume you have some expression, okay, you have some expression E, and that expression contains only, if that expression contains only union, intersection, okay, complement, okay, these type of things, if this expression contains only these type of things, okay, then how to find E complement? Then this is the idea, how to find E complement. Okay, in this type of situation you can apply the De Morgan law. Okay, so here I can apply De Morgan law. So when to apply De Morgan law, you have some expression, this expression contains only union, intersection, A complement A. Basically in this expression E, you should not have symmetric difference, you should not have difference. So this De Morgan law you can apply for union comma intersection only. Okay, so if you have this type of scenario that E has union, intersection, complement and all these things, okay, only these things must be there. Okay, now in this situation, how to find E complement, that you can do using De Morgan law. What you can do, so to find the E complement, what you can do to find E complement, this is what you can do. You can change the intersection to union, you can change the union to intersection, and if there is A complement you make it A, and if there is A then you make it A complement. So this is the idea, only this is the idea you have to apply. For example, let's take one example. If I give you A union B complement intersection C whole complement, okay, so what that will be, whole complement. So what that will be, you can notice here what is E. So first of all, here the E is this A union B complement intersection C. This expression is E, and we are finding E complement. This is the question, E complement. You can notice in this expression E, we only have union, complement, intersection, only these things we have. So you can very easily find E complement. All you have to do, this A will become A complement, this union will become intersection, okay, this B complement will become B, and this intersection will become union, and this C will become C complement. Okay, so this will be your E complement. That's it. So this is the answer. Also let me tell you, okay, this is important, that also, okay, you have, there is something called precedence. There is something called precedence of set operations. What is precedence of set operations? So the precedence of set operation is like this. So the highest priority is given to a complement. So the complement has the highest priority. Then the priority is given to intersection, and then the priority is given to union. Okay. So basically this is the order of priority. This is the order of priority. Means first, okay, it means intersection has more priority, okay, than union. What this means? This basically means like this. If I write like this, let's assume A union B intersection C, then what this means? Should this mean like this? Should I do union first? Should I do union first, or should I do intersection first? Should I do union first, or should I do intersection first? Okay, so you can notice intersection has more priority than union, so I should do intersection first. Okay, so this is the idea. So this is the idea of a priority, means precedence of set operations. So I can say intersection has more priority than union. So I can say whenever you have this type of thing, then what you should do? Should I do intersection or should I do union first? So you can clearly see that you should do intersection first. Now on this example, on this thought, okay, I can ask you very this tricky question. Okay, just understand this question. I am giving you expression E, and this expression E is like this. Okay, this expression E is basically A union B intersection C. Then what is E complement? What is that? Okay, so just find it, pause the video and find what is E complement. See, okay, let's see what is the idea. I told you that in this E you only have intersection comma union, so you can apply De Morgan law, because to apply De Morgan law you must only have union, intersection, these type of things. You should not have set difference, you should not have symmetric difference if you want to apply De Morgan law. So here you can apply De Morgan law. If you apply De Morgan law, then what will happen? This A will become A complement, this union will become intersection, this B will become B complement, this intersection will become union, this C will become C complement. Okay, and I told you that intersection has more priority. Intersection has more priority. So is this the correct answer? Just think about it. Can I say is this the correct answer? No, this is actually wrong. Okay, so this answer is actually wrong. This is the wrong answer. Why this is the wrong answer? This answer is actually wrong. Why this is wrong answer? Because see, this is the expression E, and in this expression E, okay, first you understand the operation, the expression E. In this expression E, you can notice this is E. So I can say that intersection has more priority than union. Intersection has more priority than union. So this expression I can write like this: A union B intersection C. Now you find E complement. Now very simple. This A will become A complement, union will become intersection, B will become B complement, intersection will become union, C will become C complement. Okay, so this will be the E complement. So here E complement will be this. This is the correct answer. Okay, because remember, first you understand the expression. This is the given expression. First you understand this. Okay, before you find E complement, you must understand E, and this is E. Now you can find the E complement. So answer will be this. Okay, so don't make this mistake. If I give you this expression, now don't blindly find E complement. Before finding E complement, just understand what is this, what is this E. Okay, so these are the set identities. We have seen all of them. So all these set identities we have seen, okay, like commutative property, union intersection are commutative, A union B is equal to B union A intersection B is equal to B intersection A, union comma intersection, these are associative. Distributive property we have seen, okay, double complementation, A complement whole complement is A, okay, De Morgan law, identity law, idempotence law, domination law, all these things, all these rules we have seen. One thing you can observe that, okay, these rules we have already seen in the mathematical logic. Okay, these rules that we are looking at, okay, that we are studying in set theory, we can also see that these type of things, these type of rules we have already seen in the propositional logic. So what is the comparison of propositional logic and set theory? So for example, in propositional logic, okay, in propositional logic we have propositions. So here I can say that what we have in propositional logic, and in set theory we have set. So here we have set, here we have proposition like P, Q, R. These are propositions. Propositions means statements which are true or false. So here these are propositions, means statements which are true or false. And here in set theory you can notice this P, Q, R, these are set. First of all, this is the difference. These are set. Set means collection of elements. So here in this set theory, P, Q, R, these are set. And in this propositional logic, these are basically proposition. Proposition means statement. Now you can notice this rule we have seen in propositional logic. For example, P or true, that is basically true. Similarly, P and false, that is basically false. This type of rule we have seen in propositional logic, and this type of similar rule we have seen in set theory also. In set theory, if P is a set, then what is P union universal set? P union universal set is universal set, and also P intersection phi, that is basically phi. So you can notice there is a similarity here. So okay, let's see the similarity between propositional logic and set theory. So in the propositional logic we have propositions first of all. Okay, remember, in the propositional logic we have propositions. I can write here. So here we have propositions. Propositions, these are statements. These propositions are basically statements which are true or false, and in this set theory we have sets. Okay, the second thing, okay, here I'm just telling you the similarity. Here what we have true, this true is similar to universal set. Okay, so this true is similar to universal set. This false, this is similar to empty set. Okay, and also you have, for example, P and Q, this is the conjunction. Conjunction is similar to intersection. Conjunction is similar to intersection. Okay, and also we have, for example, union. For example, here we have disjunction P or Q. This is P or Q. Here we have union P union Q. Okay, here we have negation. Here we have negation of P. Here we have complement of a set. This is the complement of a set. Okay, here also we have symmetric difference. Here also we have symmetric. So basically here we have XOR. Here we call it XOR, and here we call it symmetric difference. The name is symmetric difference. Okay, these are the similarities. Okay, these are the similarities of propositional logic and set theory. Now you can also see that these type of rules, for example, this now, okay, one by one I am telling you, like this rule we have seen, identity law. Okay, this is the identity law in propositional logic, like P or false, that is basically P. Okay, P or false is P. Similarly, P and true, that is basically P. This is the identity law in propositional logic. We have already seen this identity law. So this false is the identity element for disjunction. This true is the identity element for conjunction. This type of similar thing we have seen in the set also. If S is a set, if S is a set, then what is S union? Okay, S union phi, that is basically S, and what is S intersection universal set, that is basically S. So I told you that false is similar to this empty set, and this true is similar to this universal set. Similarly, you can notice another property. For example, this property P intersection, P conjunction. This is the conjunction. So P and false, that is false, and P or true, that is true. Okay, this is the domination law. Okay, now next, here what we have set. So if you do set intersection phi, that will be phi. If you have set union universal set, that will be universal set. Okay, so you can notice, okay, for every rule that we have, every rule that we have in propositional logic, okay, similar rule we have in a set theory. For example, in propositional logic we have this P and P or Q. P and P or Q, what is that? P and P or Q, that is basically P. Similarly, P or P and Q, okay, that is also P. This is the absorption law in the mathematical logic. Similar rule we also have in set theory. So for example, S union S intersection T, what that is? That is basically S. S union S intersection T is S. Similarly, S intersection S union T, that is also S. So this absorption law we have in mathematical logic also. This absorption law we have in set theory also. Okay, so this is the similarity between mathematical logic and set theory. Okay, so all the rules we have seen, and these two are also important. We have already seen them. So what is the symmetric difference? A minus B. This is another symbol, A minus B. This is the symbol for symmetric difference, and it simply means that A intersection B complement. Okay, also we know that A minus B is same as B complement minus A complement. This we have seen in the last class. In the last video we have seen this. Okay, and what is symmetric difference? This is symmetric difference A exclusive or B, or asymmetric difference B. That basically means A minus B union B minus A. You can also write it A union B, A union B okay, minus A intersection B. So this is how you can write it. All these things we have seen in the last video. You can watch that video. That video is very important. Okay, it is called understanding set operations. Okay, so these are the set identities that we have.